Okay, so the plan for today is to continue with the chapter 4 PowerPoint. Um, I mentioned last week that I had planned to post a supplemental recording. I ended up deciding that I think it'll be better to post it this week. I would like to get a little further in the chapter 4, and then maybe we'll gloss over some points and hit some kind of less important points or extra examples or something in the supplement. Just because chapter 4 does kind of lay the foundation, number one, for chapter 5 and chapter 6, but also because chapters 4 through 6 can also be a little more abstract. So I think just going through it in a class lecture where you have the ability to ask questions or clarification will work a little bit better. And then we'll kind of go through the main material in the course lectures, and then some extra examples and things in the supplement. So I'll have that up later this week, and that should get us pretty much back on track with the schedule. We also do have a makeup day built into the schedule coming up that will also kind of get us kind of back on schedule. So we haven't had a snow day yet, and kind of based on how it's looking, maybe we won't have a snow day, so we can make use of that makeup day by just taking a little more time going through some of this material. The quote of the day for today is from a guy, Nassim Nicholas Taleb. He was a hedge fund manager. He wrote a book called The Black Swan. Has nothing to do with that ballerina movie. It was about kind of strange things that can happen in economics, but also just kind of generally. And one of the quotes from his book that I liked is this quote that, and we'll actually see it in today's PowerPoint, but I'm including it as the quote of the day for the other classes as well, that the minds of the gods cannot be read just by watching their deeds. So there's so much of, well, essentially all of science is we observe something in the world, we look at what we observed, we try to generalize from there, we try to abstract away from those details and come up with a general rule for how the world works. And we do a lot this in math as well. We solve 10 different algebra problems, and we think, okay, I solved 10 different linear equations, maybe I can abstract away from that and come up with a general strategy to solve linear equations that will work well. And if we're basing our generalizations on data and evidence that we've gathered from the world or from our experience isn't complete. So we always have to keep that in the back of our mind, that there could be important pieces that we just haven't seen yet that don't factor into our model. The physicist Richard Feynman, he has this really amazing interview. I think he sat down with this interviewer for like an hour or two or something, and they just went back and forth with all kinds of interesting questions and discussions. So Nobel laureate physicist, he is the guy who came up with quantum electrodynamics and Feynman diagrams and some of these really important ideas. And he kind of likens the process of scientific inquiry to watching gods play chess. So he says, imagine that you're like this little human and you're watching gods play a chess game, but you can only see like one little corner of the board, and you start to, you start to establish rules like, okay, pawns can only move forward, and okay, the bishop, when I see the white bishop, it's always on the same color square. And so you start establishing these rules, and you from observation you develop a general theory, and then all of a sudden you see like a pawn capture en passant or something. It's like, oh wow, that was something I didn't expect to happen. That's a very rare occurrence, and I have to adapt my model to that. So you can look up Feynman's chessboard analogy, and I'm sure on YouTube or something that'll come up. Or another one, Isaac Newton with his shiny pebble analogy, where he talks about, I think all of these kind of fit in the same genre. He talks about, the in a sense, kind of that we always think that our science is like so cutting edge and so cool and everything. And Newton, arguably maybe one of the best scientists in history, kind of likened his discoveries to, he's walking along a beach and like staring at all the little pebbles, and he finds a new pebble that's a little shinier than the current pebble that he has, and he's all pleased with himself, and he doesn't see the ocean that's right next to him to be discovered. So so I think all of this just, brings into perspective how much there is to be known about the world. And even if we're being very careful and following the scientific method and using good data analysis techniques and so on, we always, I think, have to approach things with a little bit of humility and realize that, as George Bach says, as is kind of the motto for the course, all models are wrong, some models are useful. And particularly as we're going through probability and we're looking to eventually get to the point where we're developing models that will hopefully yield kind of a higher level of understanding, always being a little bit humble about our statements and accepting the fact that we could be making a statement that is in some sense factually incorrect, even if we have really good evidence for it. Okay, so unless there are any questions, I think I will just jump back into the chapter 4 PowerPoint. I'm going to get my windows coordinated here. Zoom is now yelling at me for having one window overlapping another one. The robots are already ordering us around. Okay, so and just a heads up, I do have my chat hidden because I have, when I'm in full screen, otherwise it'll cover something up. So if you have a question, just unmute yourself and ask. So just a quick recap of last time. We introduced the idea of probability, and the big fundamental shift, just to recall, was in chapters 2 and 3 especially, I suppose somewhat in chapter 1, we really had the idea of we're going out into the world, we're gathering actual empirical data, empirical evidence from the world, and we want to do something with that. In chapters 4, 5, and 6, we're really taking a completely different approach. We're taking a completely different look at this idea of probability or statistics or kind of understanding the world. And we're really forgetting about the real world altogether, and we're moving into a system of abstraction, of mathematics, where we're simply talking about a mathematical structure. We call this mathematical structure probability or randomness, something along those lines. It would probably call this whole genre probability theory. And as a mathematical structure, it doesn't have to obey rules of the real world. We don't have to have a solid interpretation of what this means relative to some real world experience. It has certain rules, certain axioms or premises that it follows, and certain theorems or certain results that can be built upon those premises, those axioms, using logic and coming up with theorems and so on. This part of the course is going to feel much more like an algebra course, a calculus course, something like that, than maybe chapters 2 and 3. And for that matter, chapters 7 and 8 at the end, when we try to combine these two ideas, we try to build on this theoretical foundation we've developed and try to somehow match that over into the real world. I also talked a little bit last time about the idea of randomness, and that when we try to take an abstract mathematical structure and apply it to the real world, that's a philosophical argument that needs to be made, is how ought it be applied, when ought it be applied, and if we want to make inferences, if we want to say on the basis of this structure applied to the real world, I guess that this is going to happen in the future, or I guess that this is going to happen if you try, in your physics experiment, rolling a ball down a hill with a different slope than you've tried already. What do we mean by that, right? How ought we be making those guesses? And that is a deep and non-trivial question. So, but for right now, for chapters 4 and most of 5 at the very least, we're going to kind of avoid that question. We're going to say, okay, we're just building up a mathematical structure. This is basically like an algebra course. At the end of chapter 5, we'll talk about Bayesian statistics. And that'll be a short foray into this other philosophical way of thinking about probability and chance. And then when we get to chapter 7 and 8, we'll be discussing things that are really strongly in the realm of what we call frequentist statistics. That's kind of a parallel way of thinking about applying these kinds of philosophical models or these kinds of mathematical models to the real world. So two different philosophies, frequentism that we'll be using for most of the course, that's kind of the standard in a sense, and Bayesianism that is becoming more popular and more important, particularly with things like, say, machine learning algorithms, super important ideas from Bayesian statistics being used there. But, maybe not such introductory material, or maybe we can't go quite as far with Bayesianism without some more background. So we'll touch on Bayesianism, but I think it is important to understand that the goal of chapters 4 and 5 is to build up a mathematical structure. We talked about the existence of a probability experiment. So the kind of standard example is rolling a fair 6-sided die. From now on, I'll just say rolling a die, and if I don't qualify that, that means it's fair and it's 6-sided. We roll a die, we get an outcome. 1, 2, 3, 4, 5, and 6 are the possible outcomes. So we would call that our sample space. And an event consists of a set of outcomes. So we could have the event of rolling an odd number, or the event of rolling, say, a 2. We could have, odd numbers. There are several outcomes in that event. Rolling a 2, there's one outcome in that event. We could have an outcome that's like rolling a number bigger than 0. Well, all of the outcomes in the sample space are in that event. Or we could have we can have an event like rolling a number greater than 8. None of the numbers 1 through 6 are greater than 8, so there are no outcomes in that event. So our event could consist of no outcomes, some of the outcomes, just one outcome, or all the outcomes. But that's what an event is. It's a set of outcomes. We do have to be very careful when describing events using words. So things like rolling a number greater than 2 versus rolling a number greater than or equal to 2. We just have to be careful with the wording there. And we talked about a couple examples of probability experiments and some possible events. Okay, so I think this is where we stopped last time. So what is classical probability? Or what we would probably usually just call probability. So the idea of classical probability is using sample spaces and events and outcomes to determine the probability that an event will happen. So note that our perspective in maybe chapter 2 or chapter 3 was something like, maybe I was interested in knowing, the percentage of people in the population who are over 6 feet tall. So I go out and I collect a data set of size 100 or 1,000. I measure all these people's heights. Maybe I put those heights into a frequency distribution, and I count up the relative frequency for the bins that are over 6 feet tall. That would be an empirical way of trying to get a handle on what's the likelihood that if I pick a random person from this population, they end up being over 6 feet tall. Maybe 10% of the individuals in my sample were over 6 feet tall. And maybe then I guess that 10% of the people in the population are over 6 feet tall. And maybe then I would say that if I reach into that population, choose a random person, I think there's a 10% chance that the individual I choose is going to be over 6 feet tall. Or in other words, kind of what I mean by that is, well, a 10% chance is like a 1 in 10 chance. So what I mean is, if I repeated that process 10 times, reach into the population, pick a random person, measure their height, I would expect that 10% of the time, or on one of those 10 tries, I would expect to get somebody who's taller than 6 feet tall. And on 9 of the 10 tries, I would expect to get somebody who's shorter than 9 feet tall, or who's shorter than 9 feet tall, hopefully, but who's shorter than 6 feet tall. So that's what I would expect, right? Is when I say there's a 10% chance of success of meeting the criterion for the event, I mean that I think that in 10 similar trials, I think one of the times I'll succeed and 9 of the times I'll fail to meet that criterion. In chapter 4, note that we're using sample spaces, we're using outcomes, we're using events and things like this to calculate probability. We're not saying go out and draw a sample from the population and use frequency tables or anything like that. We're saying, well, the sample space is the set of all possible outcomes. We're kind of assuming that we know, in a sense, everything about the population to begin with. And then we're asking what happens on an individual trial. So this kind of flips things on its head a little bit. This is looking at things from the opposite perspective in a sense. So for classical probability, the probability of an event, we'll call the event E. That's typically what we call it. We denote the probability of event E by P of E. So we just write capital P, parentheses, capital E. So we can think of, in a sense, the probability operator is a little bit like a function, and it takes as its input an event, a set of outcomes, and it gives as its output a number, a real number. So I take an event, a set of outcomes, as the input into this thing we call the probability function or probability operator, and it gives a number as the output. What is that number? So the probability of event E is the number of outcomes in event E. I know that an event is a set of outcomes, so I can just count the number of outcomes that are in that event. So it's just the number of outcomes that are in that set divided by the number of outcomes in the sample space, the total number of possible outcomes. So this is our calculation for probability, just the ratio of two counting numbers. We just count up number of outcomes in the event, we count up number of outcomes in the sample space, we divide those two, and that gives us a real number. Super important note here, super important assumption we're making. That all outcomes are equally likely. Very, very important. Sometimes this is a little bit trivial, like rolling a die 1 through 6, kind of standard, fair, 6-sided die. Well, yeah, 1 through 6 come up equally likely. Not a huge, earth-shattering issue in that case, but there are some, like, say, rolling 2 dice, and you might say, okay, what's the sum of the roll of 2 dice? Well, you could get anywhere from 2 to 12 as the sum, but 7 comes up a lot more frequently than, say, 2 or the 12. So we have to sometimes be very, very careful how we set up our outcomes in our sample space in order to impose equal likelihood of outcomes so that we can use this probability calculation. Sometimes this is, like I said, basically trivial, and sometimes it's much bigger. It's a much bigger deal. But an example down here, the probability of rolling an odd number is 1/2. And why is that? Well, rolling an odd number again on a standard 6-sided die, there are 3 outcomes that result in a roll of an odd number, 1, 3, 5. There are 6 outcomes in the sample space, 1, 2, 3, 4, 5, 6. Note that these are all equally likely outcomes. So the probability of rolling an odd number, or the probability of the event 1, 3, 5, is 3 over 6, or 1/2, or 50%. So we would say the probability of rolling an odd number is 1/2, it's 50%. And the way that the frequentist would think about this is, if you imagine repeating this experiment many, many times, you roll a die, you look at the result, and you say, did you get an odd number, yes or no? If you had like a yes column and a no column, and you kept a tally, and you roll this die 100 times, 1,000 times, a million times, you'd expect that after lots of rolls, very close to half of them would be, yes, we got an odd number, and half of them would be, no, we did not get an odd number. So that's kind of what we mean in one interpretation of probability. That's kind of what we mean by this. Right? As kind of a side note, that becomes, the notion of probability becomes much more complicated when we say something like, okay, a patient comes into the doctor's office and has some affliction, and we're going to give them a treatment. And, this is like the only treatment that we know for this affliction. And it has, a 20% chance of working. Well, from that patient's perspective, if you're saying, okay, do you want to go through whatever the pain, the discomfort, the cost of this treatment, it has a 20% chance of working, that patient can't say, okay, if I do this 1,000 times, then 200 times I'm going to succeed. It's like, well, no, you only get one time, right? So in that sense, the question of what does a probability mean is much more nuanced, and that's where maybe Bayesian ideas come into play. But for right now, we're going to focus more on the idea of repeated experiments and kind of long-term averaging. And that's the sense in which we're thinking about this. I think that's a pretty sensible way to think about something like a die roll experiment. We roll a die a whole bunch of times, and we'd expect that about half the time it'll come up odd, and about half the time it will fail to come up odd. Another example here, flipping a coin, heads and tails. So we could flip a heads. We could ask about the event, flipping a heads, then a tails. And be careful here, flipping heads, then tails is not the same as getting one heads and one tails on two flips. The order does matter here. So we have a sample space consisting of 4 outcomes: heads on the first flip, heads on the second flip. So heads, 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 tails, tails, heads, tails, tails. Those are the 4 outcomes. These are all equally likely. And there's one way that we can get the event, flipping a heads, then a tails, heads on first flip, tails on second flip. So we have 1 outcome in the event, 4 outcomes in the sample space, all outcomes equally likely. The probability of the event, the probability of getting a head, then a tails, is 1/4, or 25%. And again, if we repeated this experiment, flipping a coin 2 times in succession, recording the result, and we said, again, we had a yes and no column, and we said, did we succeed in getting heads then tails, or did we not succeed? We'd expect that about 1/4 of the time we would succeed. We'd expect that if we flipped the coin, did this flip, the sequence of flips 100 times, we get about 25 times that we got a head then a tail, and about 75 that we failed to get that event. We could look at something like rolling a 2, then a 3 in 2 rolls. So if we roll 2 dice or roll a die twice in succession, let's say, the event of rolling a 2, then a 3 means we have to roll a 2 on the first roll and a 3 on the second roll. So we'll call that event 2, 3. Or sorry, we'll call that outcome 2, 3. And the event just consists of that single outcome. In our sample space, we have to note that, for instance, 2, 3 is different than 3, 2. Right? Those are different outcomes. So rolling a 2, then a 3 isn't the same as rolling a 3, then a 2. So we have these outcomes. We can think of our first roll. And our second roll, kind of in a grid like this. And we have an outcome, say 1, 1. We have a 2, 1, 3, 1, 4, 1, 5, 1, and 6, 1. We have outcome 1, 2, 2, 2, 3, 2, 1, 3, 2, 3, 3, 3, and so on. We notice that outcome 2, 3 is this one here. That's the only outcome that's in our event. How many outcomes are in this sample space? When we see that we have a grid of 6 columns, 6 rows, this is a 6 by 6 grid. There are 36 unique outcomes. If I change a row and or a column, I get a different outcome, right? If I change my column, the number changes. If I change the row, the second number changes. Each of my column indices and row indices are different numbers. I don't have like a die with, 2 1s and missing a 3 or something like that. These are all unique outcomes. So I have 6 times 6 or 36 unique outcomes in my sample space. And again, with them being presumed to be fair dice, these are all equally likely. It's not like 6 comes up more often than 1 or something like that. So we have 36 outcomes in our sample space. The probability of the event is just the probability of getting this one outcome out of the 36 outcomes in the sample space. That's 1 out of 36, or a little under 3%. And again, we have to be careful, because if we wanted to talk about rolling a 2 and a 3 on 2 rolls, we would want to set everything up the same way, but we would just be counting 2 outcomes in our event from these 36 outcomes in the sample space. Probability of getting this event is 2 out of 36, or about 5.6%. Now you might say, like, okay, getting a 2 and a 3, why wouldn't I set up my outcomes like getting a 1 and a 1, getting a 1 and a 2, getting a 1 and a 3? And then why wouldn't I just say, if I'm talking about 1 and a 2, that's the same as 2 1, so I just won't write that one. 2 2 is different, 2 3 is different. Why wouldn't I take an approach like this? Well, I have to be really careful here, because note that if I just talk about rolling a 2 and a 3 and 2 rolls, so if I just took 2 dice in my hand at the same time, then I couldn't distinguish and toss them both. And I said, what's the chance that I get a 2 and a 3? Well, there are really 2 ways to get a 2 and a 3. The kind of, first a die, in a sense, could come up 2 and the second 3, or vice versa. So there are actually 2 ways to get a 2 or 3. There are 2 ways to get a 1 and a 2. There are 2 ways to get a 1 and a 4. But there's actually only one way to get a 1 1, to get a 1 and a 1, right? The first one has to come up 1, and also the second one has to come up 1. If I set up my sample space this way, where I was ignoring these repeats and just kind of counting them as the same, note that if I kind of, wrap 1 2 into the 2 1 outcome, and if I wrap 2 3 into the 3 2 outcome, basically all of these outcomes above the diagonal kind of have a partner below the diagonal, and they get kind of paired together. But the ones on the diagonal don't have a partner. They don't get paired together. We're setting up a sample space with outcomes that are not equally likely. So we don't want to do this. We have to be pretty careful when we think through problems like this and setting up the sample space. We have to be pretty careful when we set up the sample space, how we set up the outcomes, to make sure everything is equally likely. So because, for instance, getting a 1 and a 2 on 2 rolls can happen in 2 different ways, 1 then 2 or 2 then 1. But getting a 1 and a 1 can only happen one way. We have to really split everything apart. Even if we are holding two dice in our hand and we throw them both, we kind of pretend that we like maybe, you know, colored one red with a crayon and colored one blue with a crayon, and then we can think of like the red one as the first one and the blue one as the second one. Right? Even if we didn't actually color them in, we can imagine doing that and then being able to tell them apart. So that's how we really ought to set up the sample space and the outcomes. Okay, another example on computing probability. This one deals with a deck of cards, and I think I'll leave this one as part of the supplement. In the supplement, we'll talk a little bit about, I know that not everybody has, you know, used decks of cards before, so you might be a little confused about like, wait, what's a jack or a king? What's a, you know, hearts or a spades? So we'll talk a little bit about that in the supplement, introduce the, you know, values and the suits for the decks of cards, you know, kind of what they mean. But a deck of cards is another example that we often use in probability. We often use die rolls, coin flips, decks of cards, because these are structures that we've kind of worked really hard to make all of the outcomes equally likely, right? And most things that we do in life, the outcomes aren't equally likely, right? If I drive to, you know, into work today or go to the grocery store or something, like the chance, I can't say I could either get into a car crash or not get into a car crash. So it's equally likely that on this, you know, 2 mile long trip, I get into a car crash. Well, no, of course that's not true. It's much more likely that I don't get into a car crash than that I do. Or if it's true for you that it's a 50-50 shot in 2 mile drive that you get into a car crash, you know, maybe drive a little more carefully. But again, most things in life aren't equally likely outcomes. So we use a lot of these kind of derived systems or contrived systems to discuss things like probability. Okay, so probability rules. On the basis of our definition of probability up here, along with the definition of sample space, which is the set of all possible outcomes, we can make some statements about probability. The first is that probabilities are always between 0 and 1, including 0 and including 1. Well, we know that the number of outcomes in the event is greater than or equal to 0, of course. You can't have a negative counting number. You can't say this event has 3 outcomes in it, this other event has 1 outcome in it, and this third event has -2 outcomes in it. That doesn't make sense. So the fewest number of outcomes we can have in an event is just no outcomes in that event. The number of outcomes in the sample space is also greater than or equal to 0. If we're running a probability experiment, we have to be able to have something happen as the result of that experiment. If we say that we're running a probability experiment but nothing ever happens, I mean, that's kind of a silly thing to say, right? We can't talk about probabilities or events or outcomes because nothing ever happens. So the number of outcomes in the sample space has to also be non-negative. So what's the lowest the probability of an event could be? It's whenever there are 0 outcomes in the sample or 0 outcomes in the event, and there's always going to be, oh, this should be strictly positive there, greater than or equal to for the event. So we have the smallest number of outcomes in the event is 0, smallest possible number of outcomes in an event. And the number of outcomes in a sample space is always positive. So the smallest this fraction can be is 0 over positive number, which is 0. We could have an event with no outcomes in the sample space, giving us a probability of 0. So this left inequality has to be less than or equal to 0, less than or equal to probability of event. Now, what about on the right side? The sample space contains all of the outcomes that are possible from the probability experiment. The event contains a set of the possible outcomes. It could contain, half of the outcomes in the sample space, or it could contain up to all of the outcomes in the sample space. But the event can never contain more outcomes than are in the sample space. If it did, there would be an outcome in the event that's not in the sample space, but the sample space contains all of the outcomes. So that can't happen. So the biggest the event can be is the whole sample space, in which case the numerator and denominator have the same value, and the ratio is 1. So the upper bound is 1, and we could actually get a probability of event being 1 if our event happened to have all of the outcomes that are in the sample space. So probabilities are always between 0 and 1. Super important to remember this, because this acts as a pretty nice check when we're going through these next few chapters. If you do some calculations and you end up with an answer for a probability that's negative 0.2, or that's 1.7, not 1.7%, but like 1.7, well, you know that something went wrong somewhere, right? Go back, check your calculations. That's not a valid probability. Kind of as an aside, at this point, and for basically all of the course, we're implicitly assuming that our number, so in this context, we're implicitly assuming that we have finitely many outcomes. There are possibilities where we have infinitely many outcomes. So for instance, things like the number of coin flips until you flip a head. I mean, you could flip 10 tails then a head, or 100 tails then a head, or 1,000 tails then a head. And a setup like that would have infinitely many outcomes. But we're typically not going to really talk too much about those. We'll talk a little bit about them. We talk about the Poisson and maybe a tiny foray into the geometric distributions. They'll come up a little bit when we talk about continuous distributions, but they won't really impact our thinking all that much. But once we move into a situation with infinite outcomes, infinitely many outcomes, these definitions get a little more nuanced. The ideas still hold true, but some of these rules can get a little more nuanced. But for this part here, we're thinking of finitely many outcomes. We can enumerate them. We can say this one's the first one, this one's the second one, and there are, 10 outcomes or something in the sample space. If an event cannot occur, then we say its probability is 0. An event cannot occur. That means that none of the outcomes that are in the sample space are in the event. So there are 0 outcomes in the event, and this numerator is 0. So then our probability is 0 over some number is 0. If we have finitely many outcomes, we can say the opposite as well, that if the probability of an event is 0, then it cannot occur. So if the probability of an event is 0, not saying that it's pretty small and we rounded it to 0, but if it's actually 0, the only way we can get an actual 0 out of this fraction is if the numerator is actually 0, if there are no outcomes in the event. So we can flip the if then. We can make this an if and only if, in other words, provided that we're in the context of finitely many outcomes. If an event is certain, if it will definitely occur, then its probability is 1. An event being certain, if it has to occur, that means that every outcome that's in the sample space is also in the event. If there was an outcome in the sample space that was not in the event, then as the result of the probability experiment, it could be that outcome that's in the sample space was not in the event, but then the event wouldn't be certain to occur. So if an event is certain, if it will definitely occur, it has to have the same number of outcomes as the sample space. The numerator and denominator over here have to be the same, which gives us a probability of 1. And again, if we have finitely many outcomes, we can say the reverse as well. We can say that if the probability is actually 1, not like 99.7%, and we decided to round that to 100%, but if it's actually 1 for the probability, then the event has to occur. The only way to get a 1 out of this fraction is if the numerator and denominator are exactly the same. And then lastly, the sum of all the probabilities of the outcomes in the sample space must equal 1. So in other words, if I consider my sample space, maybe it has 4 outcomes in it, and I make an event, call it event 1, that has outcome 1 in it, event 2 has outcome 2 in it, event 3 outcome 3, and event 4 has just outcome 4 in it. And I take the probabilities of each of those events and I add those probabilities together, that has to equal 1 or 100%. Kind of what this is saying is that if you run the probability experiment, something has to happen. Okay, so those are the rules of probability. Again, these are nice checks, particularly this first one. As you're going through calculations in this chapter and some of the next chapters, if you end up with a probability that's not between 0 and 1 or 0% and 100%, definitely go back and check your work. Something somewhere went awry. Sorry, with all these crazy temperature swings, my allergies are picking up. Apparently all the birds think that it's spring, and my allergies also think that it's spring. Okay, so we talked about classical probability. So what is empirical probability? Well, empirical probability has kind of the feel of what we were doing in the beginning of chapter 2. Here we're using actual data, actual samples to make guesses of what the underlying distribution is, to make guesses of something along the lines of what these probabilities are or what the sample space is, something along those lines. So here we would say the probability of an event, maybe we think of that the event as being like the height of somebody in the population is over 6 feet tall. We would collect a big sample. We would make a class, people who satisfy the event, height over 6 feet tall. And, that would be one bin. And then the other bin would be the people who are not in that event, who are under 6 feet tall. We would look at the frequency for the class that represents the event. So we look at the number of people in our sample who are over 6 feet tall. We would divide that by the total frequency. We would divide that by our sample size. So the probability of the event in the empirical sense, in the data-driven sense, is the frequency divided by the sample size. So we have the law of large numbers, which kind of a little pun here. I have a little narrative here from a Sherlock Holmes story where he talks about the individual man is an insoluble puzzle, but in the aggregate, he becomes a mathematical certainty that individuals vary, but percentages remain constant. I won't read the whole thing. But this is the idea of the law of large numbers. So roughly speaking, what the law of large numbers says is that for a sufficiently large sample size, the frequency distribution that we would guess under empirical probability, under going out and taking a sample, separating that sample into 2 bins, one in the event, one not in the event, that should be close to the actual underlying frequency distribution from classical probability. If we had access to the whole population, if we said drawing an individual from the population, that's a probability experiment. The different equally likely outcomes are drawing individual 1 or 2 or 3, each of these individual people in the population, drawing that person is a different outcome. They should be equally likely if we're doing random sampling. And we can treat that under classical probability as a probability experiment, taking that sample of, say, size 1 of one person. Well, the relative frequency that, or the probability that we would guess under the empirical probability notion should be close to what we would get under the classical probability notion if we had access to the whole population. Or in other words, the sample frequency distribution should look like the population frequency distribution in relative terms, in percent terms. So something very important here with the law of large numbers. And as an aside, we're not going to prove the law of large numbers, just like we didn't prove Chebyshev's theorem until the end of chapter 5. So during chapter 5, we'll come up with some notation and some ideas that will make these proofs just go a little bit easier, just be a little more smooth and a little cleaner, rather than having to write out so much stuff, so much cumbersome notation. So we'll leave these proofs until a little bit later. But very important note here, this so-called, sometimes called the gambler's fallacy. Note that the law of large numbers does not say something like, if you just flip 10 heads in a row, then because we know that heads and tails come up equally likely, that means that you're more likely to get a tails next flip, or that like tails are due, right? You'll sometimes hear like gamblers say this, like, oh, I walked past this this roulette table and they have the little sign up there that says what the last 10 or 20 or something results have been, and oh, red came up 10 times in a row, black is due, right? So I'm going to put my money on black because and their argument is something like, well, I mean, if red and black come up, say, roughly 50-50, roughly equally likely, then getting 10 heads in a row, that's a very rare occurrence. So clearly black is due, right, to maintain that 50-50 frequency. But that's not what the law of large numbers says. The law of large numbers says, well, yeah, you might see a streak of 10 red numbers, but if you watch long enough, just by chance, you'll also see a streak of 10 black numbers in a row, right? It's not saying that, like, God is up there looking at the world and saying, oh, geez, we got 10 red numbers in a row. That's like very unlikely. I can't let 11 reds in a row come up. I've got to make the next one a black number so that we kind of restore balance to the universe or something. That's not what it's saying at all. We're saying strange things happen, but if you watch long enough, strange things will happen on the other side too. So that's what the law of large numbers says. So it's not saying that from trial to trial, the probabilities are adjusting in response to what had happened previously, nothing like that. It's saying if you watch enough trials, a strange thing can happen this way, but it'll also eventually happen the other way. And the Nassim Taleb quote that we discussed already. So subjective probability is kind of, I guess, the third that's often talked about. It uses frequency distributions based on, and I say here, I mean, I'm giving it a little bit of an undersell here, but based on opinions and inexact information. I think we could think of it as a less precisely calculated form of empirical probability. This is kind of where something like Bayesian statistics might fit in, where we might talk about probability representing degree of belief. And again, it's a philosophical discussion about what exactly this means. In the most the kind of most underselling it form, we can say, well, this is what our just kind of personal biases are that we've gone through the world, and we've have experiences in the world. And based on those experiences, we come up with models and we make decisions. And we say that, if I'm driving around and I hear the person drive up next to me with the really loud exhaust and the loud music playing and the fancy sports car, I'm probably going to hang back because I don't want them to crash into me, right? I think that they're a more dangerous driver because of these things that I say. Now, have I gone out and done a very careful, calculated study? Probably not. Particularly if I don't have a loud sports car and play my music loud, I'm going to be like, oh, that person's more dangerous. But maybe the person who looks like me, who drives a similar car to me, that was driving crazy the other day, maybe they don't factor in so much into my motto. I say, oh, that's just one goofball, right? But the person with the purple car and the loud exhaust that I saw goofing off, I'm like, oh yeah, see, there's another one of those crazy sports car people. I got to watch out for them. So I think on one extreme, that's where we can think of subjective probability, but we can actually kind of make an argument on the other extreme for something like Bayesian statistics, where we have to impose some kind of prior knowledge on the system, and then we update that prior knowledge on the basis of data and facts and mathematical structure. So this can kind of run the gamut, I suppose, in the sense in which we're discussing it, from that extremely non-scientific way of looking at the world, up to something that's quite scientific. Okay, so that wraps up the beginning of chapter 4. Any questions up to this point? Okay, just give me 1 second. Okay, moving on to the next section then. Section 4.2 on the addition rule. And kind of as an aside, just a heads up, in chapter 4, Bayes' theorem is discussed a little bit, but we're actually going to leave Bayes' theorem to the end of chapter 5. I think that the proper way to discuss Bayes' theorem really is after we discuss some of the more general notions of probability in chapter 5. Then we can really give it a more of a proper introductory treatment. So a couple of important ideas that we need to get out of the way. The first is the complement of an event. So we're working our way up to the addition rule, a theorem, a property, something like that we're going to use to help us with probability calculations. The first idea is that of a complementary event. So the complement of an event, which we denote in several different ways, depending on which textbook or which supplemental resource you're using. Sometimes the complement of an event is denoted with a horizontal bar across the top. I tend to not favor this notation, mainly because it looks kind of like X bar. It looks kind of like our notation for average. I mean, an event with a bar over it, the context is different, but it just kind of, X bar is such a ubiquitous thing in stats. Why are we going to use a bar again? But you'll see that sometimes. E superscript C for E complement. That's a pretty common one. Or E prime is another fairly common one. E with a little apostrophe next to it, denoting the complement of E. So I'll typically use E superscript C because I think it's the least ambiguous of all of these. So the complement of an event is the set of outcomes that are in the sample space, but not in the event. So we know we have a sample space consisting of all of the outcomes that are possible. We have an event that consists of some of the outcomes, perhaps none of them, perhaps all of them. But we typically think of an event as some but not all of the outcomes in the sample space. And then its complement is all of the outcomes that are in the sample space but not in the event. It's all of the possible things that could happen from the probability experiment that do not satisfy the criterion for the event. So for instance, if the event E is getting heads on a coin flip, E complement might be getting tails on that coin flip. If the event E is the Steelers win the Super Bowl, a little late at this point, but E complement would be the Steelers do not win the Super Bowl. to help us out a little bit with some of these events and complementary events calculations, we have a visual representation called a Venn diagram. So here's a simple Venn diagram. We have a rectangle representing the sample space. So I think of the rectangle as kind of containing all of the possible outcomes that can come out of a probability experiment. It contains all the outcomes in the sample space. The size of this rectangle or its dimensions or whatever is irrelevant. It's not like if I have more outcomes in the sample space, I would draw a bigger rectangle, or that I would make it a square under some circumstances. It's irrelevant. It's just a pictorial representation. I have an event that I'm interested in. This event contains, let's say, some outcomes. It could contain no outcomes, but let's just suppose that it contains a couple outcomes. Maybe outcome 1 and outcome 4 are in the event. And maybe outcome 2 and outcome 3 are outside of the event, but still in the sample space. So my event is a circle inside the sample space. And again, it's just a circle. It's not a bigger circle if we have more outcomes or a smaller circle if we have fewer outcomes. It's just a circle. It's just a diagrammatic representation. But what it does is it cordons off some events or some outcomes that satisfy the criteria for the event, and it separates them from some other outcomes in the sample space that do not satisfy the criteria for the event. So for instance, we might have a sample space for a probability experiment rolling a die. This sample space contains the outcomes 1, 2, 3, 4, 5, 6. We might be considering an event rolling an odd number. This event consists of the outcomes 1, 3, 5. So inside of my event circle, I have the outcomes 1, 3, 5. Outside of that event, I have the outcomes 2, 4, 6. And note that collectively, the set of all outcomes that are outside of my event E is the complement of that event E. So the complement of the event 1, 3, 5 in this context would be 2, 4, 6. Or the complement of rolling an odd number, I can see, okay, 2, 4, 6, I could describe that as rolling an even number. So the complement of rolling an odd number would be rolling an even number. Or in other words, if you don't roll an odd number, then you must roll an even number. Complementary events. Well, the probability of an event plus the probability of its complement has to be 1, right? Complementary events combined are exhaustive. The two events together include all of the outcomes that are in the sample space. If you doubt this, think of, probability of the event plus probability of the complement of that event. Well, this is the number of outcomes in E over number in the sample space plus the number of outcomes not in E over number in the sample space. Clearly, these two have to sum to the number in the sample space, right? So we just get number of outcomes in the sample space over number of outcomes in the sample space. This ratio is clearly 1. Numerator and denominator are the same. We've counted every outcome that's in the sample space exactly once. It's either counted on the bit that's in the event or it's counted in the bit that's not in the event. So the probability of the event plus the probability of its complement has to be 1. So, I mean, I guess that's a little bit nice, but where this can really be helpful is that we can compute the probability of an event by computing the probability of its complement. We can switch back and forth and decide to compute whichever one is easiest for us to compute. The probability of an event is 1 minus the probability of its complement, or I suppose probability of the complement is 1 minus the probability of the original event. But if we're interested in finding the probability of an event and I say, oh, that's going to be a really annoying calculation to do, I might ask myself, well, is the complementary event any simpler? If it turns out that the complementary event is simpler, maybe I'll compute its probability, subtract from 1, and go kind of this slightly roundabout way to avoid doing the difficult calculation of directly computing the probability of the event. Okay, so we'll start with kind of a trivial example where this formula, this idea won't really get us, it won't be super helpful, but just to illustrate how it might work. And then we'll look at an example where it'll be more helpful. So what's the probability of rolling an odd number? Well, we could reimagine this as, again, 1 minus the probability of the complementary event, 1 minus the probability of rolling an even number. If we don't roll an odd number, we must end up rolling an even number. I know the probability of rolling an even number is 1/2. 3 ways to roll an even number over 6 sides on the die. So 1 minus 1/2 is 1/2, and that's exactly what we expect for probability of rolling an odd number. Again, didn't really save us time in this case, but just going through the motions of how we might apply this in a simple case. Probability of rolling a number greater than or equal to 2. So what's in this event? 2, 3, 4, 5, 6. Well, that's 1 minus probability of rolling a 1, but I know there's only one way out of 6 to roll a 1. So I get 1 minus 1/6 or 5/6. This was maybe a little bit easier. It's a little easier to count the number of outcomes in an event with only one outcome than it is for an event with 5 outcomes. Probably not a whole lot easier. But what if I said something like this? On a roll of 3 dice, find the probability of rolling a sum bigger than or equal to 4. If I think about this event, this criterion here, the sum of the numbers on the 3 dice is bigger than or equal to 4, there's a whole lot of rolls that result in a sum bigger than or equal to 4. 1, 5, 6, 2, 4, 1, 3, 5, 5, 6, 6, 6, 6, 4. Lots and lots of rolls that I can think of where the sum is bigger than or equal to 4. Right. I mean, obviously, any roll that has a 4, 5, or 6 in it at all automatically satisfies it without even much more thinking. I think any roll with a 3 would satisfy it, right? Because the other two, the smallest they could be is 1 and 1, and 3 plus 1 plus 1 is actually 5. So any roll that even has a 3 or bigger anywhere in it, or any sequence of rolls that has a 3 or bigger anywhere in it, automatically works. What about a 2? Well, if I had a 2, if I even had 1, 2, the smallest the other 2 rolls could be is 1. 2 plus 1 plus 1 is 4, and that actually is also a sum bigger than or equal to 4. So if anywhere in my sequence of rolls I have a 2, 3, 4, 5, or 6, I end up with a sum bigger than or equal to 4. Well, what does that mean? That means that the only roll, I think, that does not satisfy this event is the roll, the sequence 1, 1, 1. I think that's the only one where I have a sum less than 4. It's much easier to analyze that event than to analyze or than to count all of the other rolls. It's much easier to realize that, wait, the only way that I can fail to meet this criterion is if I get the roll 1, 1, 1. And as kind of an aside here, I'm thinking of, I have like my first roll, my second roll, And I can almost think of my third roll as like going back into the screen. So I had like a cube where one edge is indexed 1 through 6. It's another orthogonal index edge is indexed 1 through 6, and then the third orthogonal edge is indexed 1 through 6. This cube is going to have like little mini cubes in it. And it's going to have 6 cubed little cubes. Right? 6 times 6 times 6. Or you can think of it, another way to think of it is like a 6x6 grid, but then copied behind itself for 6 copies, copied 5 times for a total of 6 copies. And again, the only way that I could get a sum strictly less than 4 is if I got a sum of 3 from the sequence 1, 1, 1, from this box all the way up here in this corner. So there's one outcome in the event, 1, 1, 1. There are 6 cubed outcomes in the sample space. These are equally likely because of the same arguments that we made back here. Those same arguments apply here, even though we have 3 rolls instead of 2. So the probability of rolling a sum less than 4 is 1 over 6 cubed. And then I can subtract that from 1. I can avoid counting all of these tons of outcomes that do satisfy the event. And this is about 99.5%. Any questions so far? Okay, so the next idea that we need to talk about for the addition rule is mutually exclusive events. So we say that 2 events are mutually exclusive if they cannot both occur at the same time. In other words, if they share no outcomes in common. For instance, rolling a 3 and rolling an even number would be mutually exclusive events. But something like rolling a 3 and rolling a number less than 5 would not be mutually exclusive events. If we did actually get a 3, we could simultaneously satisfy the event rolling a 3 and rolling a number less than 5. Or, for example, being a basketball player and being in the chess club, most likely not mutually exclusive events. Okay, so the addition rule, when 2 events are mutually exclusive, then the probability of this new compound event, A or B, just becomes probability of A plus probability of B. So consider that I have 2 events, A and B. This could be event A is rolling a 3 and event B is rolling an even number, or event A is being on the basketball team and event B is being in the chess club. I could combine these together to make a compound event, A or B. And as an aside, I'm using the inclusive OR here. So the criterion is that, maybe we call this event E. This event is satisfied if either the criterion for event A is satisfied, or the criterion for event B is satisfied, or if both criteria are satisfied. So if you're in A, then you're in the event A or B. If you're in B, you're in the event A or B. And if you're in both events, you're in the event A or B. So how do we figure out the probability of a compound event like this? Well, if our two events A and B are mutually exclusive, in some sense, the probability operator distributes over the or kind of connector or conjunction as a plus. This is in a sense a distributive property, right? The probability hits each of the components that are connected by some kind of binary operator. So probability of A or B equals probability of A plus probability of B, but that's only if we're mutually exclusive. If not, if we're not mutually exclusive, what's the problem with writing this? Well, let's take a look. Let's suppose that we have a couple of kids who are basketball players, a couple of kids who are on the chess team or chess club, and then a couple of kids who are on both. So I'll draw them maybe like this. So when I'm computing probabilities, when I think back to my original definition of probability, I'm asking what are the number of outcomes in some event? Or in other words, I'm saying, okay, I have these students standing here. I say, if you're on the basketball team, stand up, and I count the number of people who stood up. And let's think about, instead of probabilities, let's just forget about the denominator for the time being. We have a number of folks on the basketball team, right? Anybody who's partially green is going to stand up, and we say, hey, if you're on the basketball team, stand up, and we count them. Okay. If I say, hey, if you're in the chess club, stand up, and I count those people, but if I want to know the number that are on the basketball team or the chess club, if I say, hey, stand up if you're either on the basketball team or on the chess club or both, these 7 people are going to stand up. So this number is going to be 7. This number is going to be 4. And this number is going to be 5. But if I add 5 plus 4, I get 9, not 7. Why is that? Well, that's because I overcounted these 2 folks. I overcounted by 1, by a factor of 1, everybody who was on both the basketball team and the chess club. So I have to subtract off one amount of these folks. So the net, they're only counted 1 time. I've overcounted them 1 too many times. I need to subtract them off to fix that. So these are the folks on the basketball team and the chess club, right? I guess I've got BC going on and AB going on. Sorry about that. But so if I said to these students, okay, stand up if you're on both the basketball team and the chess club, these 2 folks would stand up. And I see that indeed 7 is equal to not 4 plus 5, but 4 plus 5 minus 2, correcting for that overcounting. So when our events are not mutually exclusive, when it's possible for us to have outcomes that are in both events simultaneously, if I count the number of outcomes in event A and I count the number of outcomes in event B, I will have counted their overlap twice, and I only want to count those once. So I have to subtract off the overlap. I have to subtract off the probability of A and B. I have to subtract off essentially the number of outcomes that are in both A and B, because they got counted once here, once there. I've got to subtract off one of them so that they're not overcounted. Okay, so some examples. What's the probability of rolling a 1 or a 3? These are clearly mutually exclusive events. We cannot roll a 1 and also roll a 3 on the same die roll. Probability of rolling a 1 or a 3 is probability of rolling a 1 plus probability of rolling a 3. That's 1/6 plus 1/6, or 1/3, 33%, as we would expect. We could draw a Venn diagram for this. We have two different events. Note that these are two separate circles, indicating that there are no shared outcomes between them. Another example, suppose that the roster for the chess club is Alex, Bob, Chelsea, and Dave. The roster for the basketball team is Alex, Dave, Ed, Frank, Gary, Henry. And we have a strange high school where nobody has the same first name as anybody else. Suppose there are 50 total kids in the school with unique first names. What's the probability that a randomly chosen student is in the chess club or on the basketball team? So let's call event A being in the chess club and event B being on the basketball team. We want to find probability of A or B. We can draw a Venn diagram here. This outer rectangle still represents our sample space being the collection of all 50 students. We have an event, let's say, being in the chess club, this left-hand circle here. In that event are the outcomes, or the students, Bob, Chelsea, Alex, and Dave, the ones in the chess club. We have a second event that is being considered, being on the basketball team. On the basketball team, we have Ed, Frank, Gary, Henry, Alex, and Dave. But we note that these two events share some outcomes. These two circles for these two events have to overlap so that Alex and Dave can be shown to be both on the basketball team and in the chess club. So when we have a Venn diagram like this with events overlapping, that's usually indicating that there are some outcomes that are shared between them, that these are not mutually exclusive events. As opposed to when we have one like this, where the circles do not overlap, that's usually indicating that we have mutually exclusive events, that the events share no outcomes in common. And then, of course, the complement of the event being in the chess club or on the basketball team, or both, is most of the students who are neither in the chess club nor on the basketball team. They're outside of these two circles. They're kind of inside of the rectangle, but on this outer area. Again, the size of the circles, the size of the rectangle don't mean anything. It's just a diagram. So we have probability of A or B. We see these are not mutually exclusive, so we need to do probability of A plus probability of B minus probability of A and B, or probability of being in the chess club. There are 4 folks out of 50 who are in the chess club, plus probability of being on the basketball team. There are 6 folks out of 50 on the basketball team. But here we've counted Alex and Dave twice. We need to take away 2 out of 50 so that we get rid of the overcounting of Alex and Dave, of those 2 guys. This leaves us with 8 out of 50, or 16%. Note that if we had drawn a Venn diagram and we have this kind of like figure 8 shape in the middle here, or like infinity type symbol, we could just go through and count Bob, Chelsea, Alex, Dave, Ed, Frank, Gary, Henry. there are 8 folks that are in that kind of glob in the middle out of 50 in the whole school, we could get 8 out of 50 that way as well. But either way, we see that 16% of the students are either in the chess club or on the basketball team. Any questions so far? Okay, let's look at one last example in this part anyway. Suppose we have a study that collects data on pet ownership and it reports the following results. I saw this in an article. I think it was one of those like USA Today or something like that, not super serious research article, but they reported these numbers. They said 37% of US homes own at least one dog, 30% of US homes own at least one cat, and 60% of US homes own at least one pet, cat or dog. And we might look at this and we might think, oh, well, somebody messed up the numbers here because 37 plus 30 is bigger than 60. Shouldn't we say that 67% of US homes own at least one pet, cat or dog? But if we did that, we would be assuming mutual exclusivity. If these events, owning a dog and owning a cat, were mutually exclusive, I mean, a lot of times it is, I suppose, depending on the dog and the cat, but if they were mutually exclusive, then we'd have a legitimate complaint here. Because probability of owning cat or dog should be probability of cat plus probability of dog. 37 plus 30 doesn't equal 60. Something went wrong. But I think, I think most people would agree that at least depending on the cat and the dog, that the same person could own a cat and a dog. Right? There can be overlap. There can be a home that has both a cat and a dog that is both counted in the 37% and in the 30%. So if I want to think about my sample space here, all US homes, I have my dog owners. This circle represents, if I just said, if your house has a dog in it, raise your hand, so to speak, and I count all of them. That's what's in this circle. If I said the same for cat owners, that's what's in this other circle. And there's some overlap here. If these were mutually exclusive, if these circles were like this, I'd have 37%, 30%. Adding these together would give me 67%, not 60. But in reality, I kind of understand that I have non-mutual exclusivity. There's some overlap here. And I can just kind of do a little bit of puzzle solving, I suppose. If these were separated, 37 plus 30 would have to be 67. How much overlap does there have to be to make this total 60% instead of 67? Well, this has to be 7% of homes own at least one cat and at least one dog. Since a total of 37% own at least one dog, there have to be 30% of homes that own at least one dog and no cats. Since 30% of homes own at least one cat, there has to be 23% that own at least one cat and no dogs. And then 60% of US homes own at least one pet, cat or dog. So 60% is what's accounted for in this figure here. Which means by complementary event, the percentage of homes that own neither a cat nor a dog, that have no pets, at least none of these pets, is 40%. I didn't use any formulas. I just used the Venn diagram and just almost like muscling through it, like puzzle solving almost, to get this result. I could also have gone through and carefully used my basically taken an algebraic approach, carefully used my formula for the addition rule with non-mutual exclusivity. What's the probability that somebody owns cat and dog? Well, so here we could say from our formula, we can't stop here because we don't have mutual exclusivity. We need to tack on this extra little bit so that we adjust that that total counting number. This is a D. Looks a little too close to a P. So probability of cat or dog, probability that somebody owns at least one of these pets is 60%. I'll leave the percentages off, but probability of cat, if I said, okay, if your household owns a cat, raise your hand, so to speak, I'd see that 30% of them indicate they own a cat, 37% indicate a dog, and we could say like minus X or something, solve for X. I'm really not having a good writing day today. 30 plus 37 minus 60. I added X onto the left side. I subtracted 60. So I see X has to be 7%, or this overlap, this probability of cat and dog has to be 7%. So I've now verified this number with, without just kind of the brute force or puzzle solving technique. I have just gone through the probability rules and theorems that we've developed and shown that number. You could do it either way. Now, there is another idea that if we have an event and we separate it based on another criterion into kind of two sub-events, we have another one of these kind of sample space kind of ideas. So just kind of as an aside, if I think of having an event like owning a dog, I could segment that. I could split it into two pieces based on, say, cat or no cat. So I see that, for instance, probability of dog equals, well, on the left side over here, probability of dog and cat, plus on the right side, probability of dog and no cat. I can take an event like dog, like owning a dog, that's going to have a bunch of different outcomes in it, a bunch of different individual households in it. And then I could take those households that own a dog and I could split them into the households that also own a cat, put those over on one side, and those households that do not also own a cat, put those on the other side. If we wanted to dig a little bit deeper, if we wanted this to feel more like a mathematical proof than a hand wavy argument, what are we really doing here? We're really splitting the event dog into dog and cat, or dog and no cat. We have probability of one event or another. These are clearly mutually exclusive because to satisfy the first event, I must own a cat. To satisfy the second event, I must not own a cat. I cannot be in both places at the same time. I can't simultaneously own and not own a cat unless I'm Schrodinger, I suppose, but Schrodinger's long dead. So nobody alive today can simultaneously own a cat and not own a cat. Mutually exclusive means this or turns into a plus. So if I wanted to really drive it back to those fundamental probability rules, I could. But I think, basic logic kind of can also get us here. And that's what I'm using over here, is to say the probability of dog and no cat is probability of dog minus probability of dog and cat, or 37% minus 7%, or 30%. That's where I get that number from. We could do exactly the same. Oh, I scrolled and I meant to scroll over here. I scrolled over my PowerPoint. We could do exactly the same idea, but having our overall event being cat owners who also own a dog or who also do not own a dog, and just flipping the roles of cat and dog over here, and then plugging in the appropriate probabilities gets us this 23% for the folks who own only cats and no dogs. Again, we could do a kind of like brute force using the Venn diagram, as well as maybe a little bit of like problem solving or puzzle solving. What does the overlap have to be to make the numbers work out right? Or we could go through all of the algebraic details. Personally, I like the Venn diagram method, the puzzle solving approach, a little better. But some people don't like that because it's a little more amorphous. It's like, okay, I don't have a set. I can't give you a set of 4 steps that if you like do these steps, then you'll get the answer. You have to kind of, wrestle with it a little bit with the information you're given and so on. But if you want a more algorithmic approach, you can say, okay, just use the formula, plug in the components you have, and for the components you don't have, either do something to figure out what they are, or solve for them based on the formula. Yeah. But we do see that, even at first glance, this statement might seem contradictory. 37 plus 30 is not 60. It actually does work out, and it's that non-mutual exclusivity that's the important factor here. Any questions on this? Can I see somebody in chat? Okay, yeah. Any questions on this? All right. So